Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we are starting the last session of the workshop, and it's a talk by John Colomos with artistic stylization of consumer media collections. Over to John.
Okay, thanks for the introduction. Okay, so I'm John Colomos from the University of Surrey. I'm a lecturer there. I've been there for just over 2 years now, and the work I'm going to present today is briefly a summary of what our group's done in those 2 years, and I'm going to focus in particular on one project, which is on the artistic stylization of consumer media collections. So this is another talk where we've got the computer graphics and the computer vision coming together, and the graphics posing new requirements that motivate new work to be done in computer vision. And in particular, I'm going to present a video segmentation algorithm. So more on that later. So just some brief motivating context. I'm sure we've all been in the situation where we've been in our loft and come across an old box of media, of old photos, and started to leaf through them and had a very enjoyable experience reminiscing. And those photos have a lot of value to us. They encode our past memories and experiences, but they're largely useless because they're inaccessible and they're not in a structured form. And indeed, we've probably got old videos as well, which arguably might even be more useless since we can't play them on normal hardware. Now, of course, we have digital photography and digital photo frames and the like to present our media, but are our personal media collections really any more accessible? The work I'm going to present today focuses on something we've developed with some HP Labs funding we call the digital ambient display. And this is looking at ways to add value to those media collections through structured presentation of the media and also stylization of that media in artistic forms. Now, what I mean by artistic stylization is transforming images or video, and video is the focus of this talk, into paintings or cartoons, that kind of thing. So before I go into detail on that project, I just want to summarize some of the other work that we've done. Broadly, our group is looking at ways to increase the impact of visual media collections, of image and video collections. We do that through either techniques for visually searching those collections or techniques for either presenting those collections in different ways or for editing those collections. One of the projects we've looked at recently is a new segmentation technique distinct from that I'll present today called TouchCut, where we have a system on a touchscreen device, and with a single touch we're able to segment an object in an image and also use that to bootstrap a video tracking process. And the idea is that enables editing on touchscreen devices. And you can see here we've selected this object and stylized the object using a simple artistic rendering filter. We've also been looking at visual search, as I mentioned, and looking at sketches for visual search. We've produced a system for sketch-based image retrieval that was the first system to adapt the bag of words framework commonly used for photorealistic image query to sketch-based image query. And we did this by introducing a new descriptor we call gradient field hog that outperforms SIFT, hog, and various other descriptors by about 10 to 15% at the task of sketch-based retrieval. I can take questions on some of these. I won't be covering these today. We also looked at sketches for video retrieval, where we sketched not only the object, but also the direction the object moved. And we used that to index a database of sports video. And the contribution there was a new probabilistic model for labeling superpixels in the video to one of many objects that have been sketched. And the way that we treated that was as a hidden label problem, trying to label these superpixels to, as I say, the objects or the null object, which hasn't been sketched, whilst also trying to produce a trajectory across a panorama of the video that increased monotonically, treating this as a state space. This was presented at ICCV in 2009. Another type of visual collection we've looked at is dance. We've got some work under review at the moment looking at a new form of descriptor for matching pose in photos of dance and also videos of dance. And this is able to work over very low resolution archival quality footage. This has also got a benefit beyond computer vision, where we've digitized a lot of dance collections and put them online for the community, and we've got a web demo of this technology. And then finally, we've also looked at visual search in, I guess, more of a traditional sense, looking at identifying photo fragments in large databases. And this is JISC-funded work. It's looking at developing a solution for visual plagiarism detection in art coursework. And it's being trialled now at 4 UK universities. And it's more of an engineering project, this, looking at cloud solutions for bag of visual word search. So that was a very brief summary. Let me go into detail now about some of the work we've been doing on these digital ambient displays. This project was motivated by the question of how we can present our digital media collections in a setting perhaps commensurate with a shared meal or a living space where the media is engaging whilst at the same time, almost paradoxically, not being too distracting. So we've all been in the situation where perhaps we've been in a cafe and we've seen a TV in the corner, it's showing a program, and we're always distracted by this program, even if we're not interested in what the program is. So is there a way of kind of hanging a video on a wall that gives us the content but isn't so distracting? And we feel that one way of doing that is to use artistic stylization techniques. So this display does a couple of things. It's not just your average digital photo frame. It presents the media in a structured way by clustering the media using keyword tag similarity and also clustering on visual similarity to create a hierarchy out of your content. So if this were a trip to London, it might cluster your photos into like London, Big Ben, Buckingham Palace, and so on. And the system will walk around the tree presenting that media. And it's also equipped with a camera, so it will dive down deeper into the hierarchy if it sees that you're interested in something it's showing. I'm not going to talk about that side of the work today. What I'm going to focus on is the artistic stylization. And as I say, this motivated some new computer vision algorithms that I'm going to present. So, because I guess many people here won't have looked into the artistic stylization literature, I'm just going to give you a very brief overview of how these techniques tend to work. I guess a lot of people would argue that artistic stylization, sometimes called NPR, non-photorealistic rendering, originated from the work of Paul Haberle in SIGGRAPH 1990. And he observed that people, when they're using digital paint programs, which really haven't evolved a lot in the last, I guess, 40 years, at least in the simple case, they can't develop these rich kind of images that we might see an artist produce in real life. And he attributed this to the large time to palette to go back to select new colours in the paint program. So he came up with this idea whereby if we wanted to produce a painting of this photo, we would click on the photo and a colour would be sampled at that particular pixel we've clicked on, and then on a canvas that shared the same geometry, a paint stroke would be splattered down, and that would be done in succession to produce a painting over time. So this is a ×10 speed up of someone using such a system. Here, not only the colour, but also the stroke orientation is being sampled from the underlying image using just a Sabel operator kind of gradient thing. And then the user is choosing the size of stroke, and obviously implicitly the ordering of the strokes as well. But this can also be automated, this scale selection, using some sort of edge strength measure or also maybe an image salience measure of some kind. So you can produce very quickly, especially when you're playing at 10 times speed, something that looks very much like a painting, but it's still a manual, semi-manual process. And if we want to extend this to video, which we're interested in, this can prove to be a non-trivial exercise. So the main challenge in creating paintings from videos is what we call, obviously, temporal coherence, which means that the strokes should basically not flicker, so they should be stable, but also the motion of the stroke should match the motion of the underlying objects in the video. So what was being shown there on that video is that these strokes were, well, this initial attempt by Levinovich was basically pushing strokes from frame to frame using an optical flow estimate. And because the strokes can move independently to the objects underneath them, they tend to pull apart and not match the motion of the underlying objects. So we're seeing motion that's not consistent with the underlying object and also not consistent within a given object. But if we look at a real painting, we can see that actually the way that artists lay down strokes is consistent within semantic regions of the object. So in this painting Around the Cake by Theobald from 1962, we can see that these strokes have been laid down consistently within this region of the image, and it immediately makes us think in terms of computer vision about image segmentation and how that could be applied to the problem. So this is a manual segmentation of that image, but not too far away with what you might expect an image segmentation algorithm to give us. So if we were to use image segments to constrain our stroke properties to be consistent, we get stability over time if we're looking at a video, and also we would get consistency within the region. And so the problem of painting a video is very closely related to the problem of segmenting a video in a temporally coherent manner. So let's suppose we're able to segment the hand of this boy over time, what we could then do is perhaps establish a correspondence between the contour of this frame to this frame, and then using something like a shape context, and then we're able to produce some sort of dense motion field which we can warp the strokes around in, effectively producing a rotoscoping system. So stably segmenting the visual structure in a video basically leads us to higher quality stylization. So this motivates the video segmentation algorithm I'm going to present today. This is work that's just been accepted to IEEE Transactions and Multimedia, so this is my chance to showcase it since it's not at a conference. The key features of this system are it's basically a multi-label COF-based segmentation approach, so a multi-label graph cut-based approach, and it incorporates not only a unary and pairwise term, but also multiple superpixel segmentations which increase the spatial coherence of the system. But of course, we also want temporal coherence, and in order to do that, we do some bookkeeping to keep a color and texture model updated as we move through the sequence. It's a progressive algorithm that goes from frame to frame. And we also have to do some bookkeeping to manage the birth and death of different regions. Okay, so this is the energy term that we optimize. First of all, I'm just going to explain how we segment a single image, and then I'm going to talk about how the motion comes into it. So we're looking here, as I say, at a unary term, a pairwise term, and a high order term that relates to superpixel segmentations of the scene. And here we're introducing notation I subscript time for the frame data, for the pixel data, and we're trying to label each pixel I in the set of pixels V in the particular frame with a label from this set here. I'm going to walk through the different terms briefly to give you an overview of how the technique works. The unary term initially isn't so exciting because the first couple of terms are kind of, I guess, fairly standard. The unary term is made up of a color model, a texture model, and this temporal model, which is the interesting part, which I'll come to in a moment. The color model is effectively a GMM learnt over time for a particular region label. So it's learnt just as a simple color model driven by the pixels that have been labeled as that region in previous frames. There's a texture term, okay, which is a standard text-on-based term. We distill a number of feature vectors from the first frame of the video in a 40-dimensional space, and we codebook that space, okay, so that each label then has a histogram of those code words that represents the kind of texture we would expect to find in that label. And then finally, there's that labeling prior that I mentioned briefly before, okay, which is basically information that's been propagated forward from previous frames, and that's the interesting part. The pairwise term is fairly standard. It just basically will penalize contrast change within a single label region. So this is seen in many papers. And the superpixel term relies on multiple over-segmentations of the video frame using, in our case, we've used mean shift and NCUT's superpixel technique. We run these algorithms with various different settings to get, in our case, 6 different over-segmentations. And what we do is we penalize situations where if we have, say, a particular label and that label lands within a superpixel, what we do is we count up how many other pixels disagree with that label, and that gives us a penalty term that we apply for that particular labeling, and that's averaged across all of our over-segmentations. I'm just going to give you a preview of the output of this algorithm, and I haven't described the motion propagation yet, just the static term. This is the source, and this is our output. Yes, yeah, so yes. So thanks to Michael Cohen for releasing this data set. Okay, so right, so this is a single frame, the source and our proposed energy term. And remember, this incorporates the motion propagation, which I haven't yet explained, so I will in a moment. I just wanted to show, first of all, the influence of the different terms. So if we just had the unary term in our optimization, obviously we can see there's a lot of spatial incoherence over here because there's no constraint there as enforced by the pairwise term. And with the pairwise term, we clean a lot of that up. We can still see some incoherence here, and especially on the finer features, some difficulties around the legs. If we include one superpixel over segmentation, we can see a significant improvement, but still we have some difficulties here around the leg regions. But then when we do incorporate multiple over segmentations, we get a much better quality definition around the legs. So this is the justification for using multiple over segmentations, because some of those over segmentations are likely to be incorrect. Okay, so moving forward then to the motion term, our first idea was to basically propagate forward the labels from frame to frame to basically initialize the graph cut on the next frame. So let's say we had a frame, and this is the result of our single frame segmentation. And I should say on our very first frame, we initialize using just the standard mean shift segmentation. Then what we do is we use the dense sift flow algorithm to compute for every pixel a new location at the next frame instance. And then we skeletonize those regions and use those as, if you like, scribbles to initialize the graph cut on the multi-label graph cut on the subsequent frame. Okay, and that gives us then a basis to segment the next frame and so on iteratively. So these are then, in this initial attempt, are hard constraints. The other thing we need to do is update that appearance model over time, the color and texture appearance. And we do that by basically updating our Gaussian mixture model over time by recomputing it over the last few time steps with a contribution weight that decays over time. And this gives us also a convenient way to detect the region birth and death. When regions appear, it means that we have allocated a label, because we've always got as many labels to allocate as we had available to us on the previous frame. We have to allocate all of those labels, and a new region will therefore be allocated one of those pre-existing labels. So that means there will somewhere be a region that basically, two regions that have been allocated the same label, and that will cause a very different Gaussian mixture model in the color space to occur. So by measuring the chi-square distance between these two Gaussian mixture models, the current one and the previous historical model, we can detect the appearance of regions and then resegment that region, again just using standard mean shift. The region disappearances or deaths are handled implicitly because we needn't use all of the labels we used on the previous frame to label the current frame. These are the results of that first approach. This is per frame mean shift, which you might, well, with a bit of help from an edge detector, which you might expect to perform poorly. This is our approach. And then this is approach from ECCV 2008 from Paris et al. So we already get an improved coherence, and this is a rather artificial example showing the region appearance being handled. So this was the first iteration of our system. But it can fail, especially when the sift flow is computed incorrectly. So what we then did is we went and enhanced it with by moving these skeletons from being hard constraints to soft constraints and diffusing them probabilistically over time rather than just propagating them forward on a per pixel basis. So given a particular region, which could be, say, for example, this region with label n, we are propagating forward, as I just described, a subset of those pixels, ON, which represent the skeleton of that region. Okay? And the system's obviously going to fail if the skeleton that's propagated is wrong. So what we do instead is we diffuse forward those labels so that each pixel has now a probability distribution over it as to which label it may obtain. In more detail, this is our skeleton then for a single region, and it contains these pixels at the previous time step, okay, and we're labeling those pixels 1 to the number of pixels in the skeleton, okay, and we're computing for every one of those pixels at its position in the previous frame, okay, we can compute for any position in the current frame the probability that label has moved, that pixel label has moved to that location. And we do that by simply centering a Gaussian on its predicted position based on that SIF flow. And that Gaussian has a standard deviation. We choose the standard deviation based on the local estimate of motion coherence around that pixel. Okay? And we do that by computing in a small window, like a 7 by 7 window, I believe it is, a histogram of motion vector directions. And we look at the entropy of that histogram. And if the entropy is high, it means there's uncertainty in that region, which means we'd also, we'd want to have a lower spread. Okay, so obviously if we do this for every pixel in the skeleton, we can sum up those contributions, and we normalize here, assuming just the uniform prior here, to get basically the probability that a particular pixel has been assigned the label from that skeleton. So that's our probability that we propagate forward and becomes this term, or an approximation to this term, which was our third term in that unary term of our graph cut. That's only taking into account the previous frame. Okay. Actually, what we do is we look at multiple frames. We look at the current frame and several frames before it, and we compute all of this basically for that frame and one before it, and then that frame and the one before that, and so on in a pairwise fashion. Okay, we can average these together, and we weight the average according to some confidence, and that's the confidence between the current frame content and the warped content we got from the SIF flow. Okay, which hopefully you're following that. Obviously, yeah. So, okay. So here's the proposed method then on that sequence. There's a URL in this paper that you can download these and the data as well. Okay, and this is a comparison then of our proposed approach to the hard assignment approach. So this is our soft assignment motion diffusion approach. This is the hard assignment. This is that Paris algorithm from ECCV 2008. And this is the Quattro et al. Algorithm from CVPR 2010. So we can see at least subjectively that there's a greater degree of coherence there. Oh, I think you've seen that result previously, so I'll skip. Again, for the moment, just subjectively, we can look at the results of the hard assignment, which was that first approach, and our proposed motion diffusion estimate. And you can see that we get rid of this kind of smearing artifact that we can see here on the legs. If we look at the quantitative data, then, and we use the Berkeley methodology to evaluate this by manually marking up frames every 10 frames so that my PhD student doesn't get too tired. And then what we do is we use basically the Berkeley methodology to evaluate how close our segmentation and various other algorithm segmentations are to that frame. We can see, interestingly, that despite this being a progressive approach, we don't have a decay over time that you might expect with accumulation of error. So these are some of the results. This is, obviously, the purpose of this was to produce artistic stylizations. So here are some kind of paper cutout styles that we presented from various videos. And these are some examples of painterly renderings that we produced from the sequence. Notice the problems with the faces, which we'll come back to. And there are, well, several minutes of this, really. These are some of the paper cutout, kind of highly abstract approaches. from that part of the work, we can see that although we've adopted a forward propagation strategy for these labeling priors, by extending this initial idea of the hard assignment to a soft assignment with motion diffusion, we don't have the kind of accumulation of error that we might expect such an approach to have over time, and also that the algorithm performed competitively relative to the other algorithms that I showed you. And we've also shown that coherent video segmentation can be applied to the computer graphics problem of the artistic stylization. Something I haven't shown you in detail, but I just presented the results for, this is published already, so you can look this up, is that we did some user studies looking at user engagement with these ambient displays, looking at a random presentation of the videos, rather like a random slideshow you'd get on any digital photo frame, a structured presentation using our semantic structuring of the media, which again I haven't had time to go into, and looking at the structured and artistically rendered version. And in all cases, we saw an improvement, a statistically significant improvement in the level of engagement based on the amount of time the user spent looking at the thing, which we measured using the onboard camera. Okay, I've got a couple of minutes left, so I just want to give you a preview of some additional results that we've produced recently, looking at the rendering of faces, which were a weakness in a segmentation-based approach. Rendering faces is an especially difficult problem for an artistic stylization algorithm because we have a very high perceptual prior on what we believe to be an acceptable rendering of a face. If we run one of the state-of-the-art algorithms for painterly rendering over a face, we get a lot of blurring here around the facial features that we would normally find unacceptable. We've created a new system that will produce high-quality portrait renderings by fitting a model to the face and treating regions independently. Another interesting thing about this system is that it learns artistic style from example. So the system can be given a photo and a painting that a user has produced, and then it will learn basically models for the properties of strokes on a per facial region basis. We get this by fitting an active shape model. And then those parameters are learned based on the underlying information we've extracted from dense feature extraction from the image. And that model can then be applied to render new images. And it can take into account shading and introduce things like complementary colour if it's been used, and produce a variety of different artistic styles. So these are our rendering outputs, and these are some of the input paintings that were produced. And in particular, the hair and the eye preservation is much better than some of the state-of-the-art algorithms. Okay, so that's my time up, I think. This work is obviously due to a large group of people. These are my students and postdocs that work in our group. And yeah, thanks for your attention. I'll be happy to take any questions.
So we have time for a few questions.
These are really impressive results, especially on the motion segmentation. A question I had, your spatio-temporal CRF model, you had quite a few potentials. How did you learn the weights, or how did you set the weights?
Okay, right, that's a good question. So I didn't talk about the inference step. Actually, the inference step for the spatial term is borrowed very heavily from the robust PN model that Vishmeet and colleagues presented in CVPR, I think 2008. And we use that to optimize on the spatial segmentation. In terms of the temporal, that's just propagated information from previous frames. So
that's for inference, but what about the weights of the potentials?
Okay, on the unary term.
Yes, on the unary you have the multiple ones, and then you have two pairwise and higher order. How did you set those weights?
Empirically, my understanding is they don't require an awful lot of tweaking, but yes, I believe that the unary and pairwise term, the weights on them are just one. I think the superpixel term took a bit of tweaking, yeah.
So do we have any more questions? Okay, Carsten.
So one question with the optic flow, did you try different optic flow techniques, or did you, because you used SIF flow, but
yeah,
but I think optic flow is really crucial, right?
Yeah, definitely.
Yes.
I mean, we tried quite a few techniques when we were developing the initial hard constraint version, like Brox and various things like this, but we just, I don't know, I've got a dim view of optical flow techniques. It was very difficult to find one that worked very well for our data, but we did find that the SIF flow was perhaps one of the more generally useful techniques, and robust, I mean. So we just adopted that in the end. But the purpose of the motion diffusion was actually to mitigate errors in the dense flow estimate.
But you never feed that back. You could potentially feed it
No, it's always fed forward. So this was commercially sponsored work, and one of the potential applications for this work to run fast enough was for video stream processing, actually. So we were kind of avoiding that by design.
Okay, so we have a last question.
So I'd like to focus a little on the artistic re-rendering. So have you explored alternative kinds of re-rendering to the, well, it looked like largely it was just recoloring all your superpixels here, but...
Yeah, so
right.
the region map that we get out is our basis for stylization, and we paint with the same algorithm for every region, but I guess we could explore a wider gamut of styles by just selectively painting certain regions or applying different algorithms, but really we've been focusing on the painterly rendering, well, and also we saw that paper cutout style, which was literally just a mean shading of the regions. So, yeah.
I think you said at the beginning something about how your starting assumption was that people's media would be more attractive to them.
Yes.
They could do this kind of stuff. I mean, is that actually true? Did you sort of get a chance to test that out?
So the validation in that respect that we did was through the user studies of engagement that I only briefly presented the results for, but that's published in Computers and Graphics, in a journal version. There's a long piece on that study. So yeah, I mean, we can say that they're more engaged with their collection. The question is whether that's just due to novelty of the effect, yeah, it's very hard to judge whether someone likes a technique more. I mean, this is the problem with the whole of artistic stylization, really, the validation aspect of it. But yeah.
It's your sort of your holiday memories or something, you're looking at. I wonder whether people want them transformed or would sort of want them untouched. I don't know. How does that work?
Well, the initial motivation was to create a system that produced a rolling visualization of your video collection in a way that didn't basically replay the video, which seems to be how things are done. So, especially with that paper cutout effect, I didn't really play the full length of it, but the paper cutout kind of morphs into another paper cutout and morphs again, and it's meant to be this kind of flowing, almost like a screensaver visualization that's less distracting than perhaps just replaying the video. I think that degree of abstraction is arguably attractive for presenting that media in a ambient setting, but whether it'd be very difficult to judge how to validate that. Yeah, we haven't looked into that.
That's a beautiful result.
Thank you.
Okay, so let's thank John again, and